In this short lecture, I want to give you some examples of bounded linear operators. More precisely, I'll be speaking about integral operators. So we will assume that we have two spaces, which I will represent by Sj. J will be either 1 and 2. So these are metric spaces. Associated to these metric spaces, I'll consider the Borel sigma algebra on Sj. And we have two measures, which are defined on the Borel sigma field. And this measure, I'll assume, just to fix ideas, that they are finite, so that mu j of Sj is finite. And here j is equal to 1 or 2. So this is the context. We have two measurable spaces. And on these spaces, we can, of course, for p between 1 and plus infinity, define the LP spaces. So the LP spaces can be defined either as the family of measurable functions such that the integral of f to the power p on Sj d mu j is finite. And just to make sure to which space I'm referring to, I'll say that this is LP of mu j. So this is the set of all functions which are measurable such that this integral is finite. Of course, when p is equal to plus infinity, we are talking about the functions f for which the supremum, the essential supremum of f is finite. And this will be represented by f infinity. So I refer to a course in measure theory just to tell you what the essential sup of a function is. And so these measures are finite. So LP is this space, but you know also that LP can be understood as the completion of the space of continuous functions. So if I represent by C the space of continuous functions and by CB the space of bounded continuous functions on Sj, then you can define, you can obtain LP as the completion of this space with respect to the norm Fp, where the norm Fp is the integral over Sj of f to the power p d mu j to the power 1 over p. So you can also define LP as you start with the space of bounded continuous function. You see that if a function is bounded and continuous, since I assumed the measure to be finite, these integrals are finite. This defines a norm in this space. This space is not complete with respect to the norm, to this norm. If you complete that space, you get what we call the space LP. And so this will be the context. And what we will be studying are operators going from LP of mu1. So what I interest in is to define some operators A, which goes from LP of mu1 to LQ of mu2. And so this is what's coming. So let's assume that we have a function k from S1 times S2 to the complex field. And what we will define is the following integral operator, A of f. So we consider function f, which is defined on S1, which is measurable with respect to B1. And we will define a measure AF, which takes value in the complex plane and which is defined in S2. So for S in S2, AF of S will be given by the integral over S1 of K S T Ft mu1 dt. Of course, we need some conditions on k for this integral to be well defined for functions f. So typically I will take, as I said, f of function LP of mu1. So we need some conditions on k for this operator to be, for this integral to be well defined, therefore for this operator to be defined. And what I want to discuss are conditions on k for a to be a function from LP to LQ. I'll start with some examples which I will derive these conditions. I will leave some exercises, and these operators will appear later when we consider some elliptic differential equations. So as I said, I have a function k which is defined on the product. It's measurable with respect to the product topology, product sigma algebra, and we have defined this operator a. Now I want to fix conditions on k for these integrals to be well defined. So let me first consider the case 1, say, in which I would like a to be a bounded operator, say from L1 of S1 to L infinity of S2. Which means that I want to find sufficient conditions on k for a to be a bounded operator from L1 to L infinity. So in order to do that, let's consider f. So in L1 of mu1, AF is defined over there, so let me write it again. A of fs is the integral over S1 of k st ft mu1 dt. And so I'm assuming that f belongs to L1, and I want an estimate in the L infinity norm of AF. So AF infinity, as we know, it will be the supremum over S in S2 of AF of S. So here is the formula of AF of S. I want to estimate this quantity, and I want, since I want A to be a bounded operator, I want to estimate the supremum by a finite constant times the one norm of F. So my goal is to find conditions on K for this inequality to hold. Well, so I need here to estimate this quantity in terms of the one norm of F. So this is clearly, so I have here a product. I want to estimate this integral with respect to the L1 norm of F. So there is not much I can do. I will just estimate this quantity by the supremum for t in S1 of k st times the one norm of F. So I'm bounding the norm, the absolute value of AF of S by this quantity. And now I have a supremum over S. So my conclusion is that the L infinity norm of AF, which is this supremum, that this is bounded. So now if I bounded AFS for each S by this quantity, so now if I take the supremum over S in S2, and if I assume that this quantity is bounded by a finite constant, I get the inequality I wanted. So the conclusion is the following. If my kernel, I will call KST the kernel of this integral operator A, if the kernel is such that its supremum over S and T is bounded, then AF defined by this identity is a bounded operator from L1 to L infinity, and its norm the norm A, it's bounded by C0, where C0 is this constant. So if I define C0 to be this supremum, what I get from these estimates is that A, it's a bounded operator, and its norm, it's less or equal than this supremum. So let's consider a second case. So case 2, I want now A to be a bounded operator from L infinity to L1. So let's say that this is case 2. So again, I will consider a function f, which is now in L infinity, and I want A to be a bounded operator from L infinity to L1. So I want to estimate AF in the one norm, and I want to bound the one norm of AF by a constant times the L infinity norm of f. So I fix a function f in L infinity mu1, so a function which is essentially bounded, and I want to estimate the L1 norm of this expression in terms of the L infinity norm of f. So again, I fix a function f in L infinity, I write AF. I want to estimate the one norm of AF. Now f, it's a function in L infinity, so I need to estimate this integral in terms of the L infinity norm of f. Well, but I can bound that by the L1 norm of k times the L infinity norm of f. Now, since I want to bound the one norm of AF, I want to estimate the integral of the absolute value of AF ds mu2 ds. I just bounded this quantity by this expression. So the integral of AF, it's bounded in view of this inequality by the integral over S2 of mu2 ds, the integral over S1 of mu1 dt of the absolute value of kst times the L infinity norm of f. So again, if I call this quantity here C naught, what I have proved is that the L1 norm of AF, it's bounded by C naught times the L infinity norm of f, which means that if this integral is infinite, A as an operator from L infinity to L1, it's bounded, and its norm, it's bounded by this constant C naught. So again, I found a sufficient condition for the operator A to be bounded from now L infinity to L1. And I leave it to you as an exercise to get conditions which guarantee conditions on K, on the kernel K, which guarantee that A, it's a bounded operator from L infinity to L infinity or from L1 to L1. So I leave that as an exercise, and now what I will do next is to concentrate in the case from L2 to L2, in which case I'll get two different conditions on K which ensure that A is a bounded operator from L2 to L2. So now I want to obtain sufficient conditions on K for A to be a bounded operator from L2 to L2. So I'll fix a function f in L2 of mu1, and I want to estimate AF in the L2 norm. So let me write again A of f as as the integral over S1 of K ST FT mu1 t. And I want to estimate the L2 norm, knowing that F belongs to L2. So let me take the absolute value of this quantity, and maybe square. And here, what I can do is to use Schwarz inequality to say that this expression is bounded by the integral over S1 of K ST square mu1 dt times ft square mu1 dt. And what appeared here, so this is just Schwarz inequality, and this quantity here is the norm of f square. So we have a bound due to Schwarz inequality of this expression. We want to estimate its norm square. So let's take the square. The norm square is just the integral of AF S square mu2 ds. So we take the integral with respect to mu2 of this inequality to get that this expression is bounded by this integral. So what we get is the integral over S2 of mu2 ds, the integral over S1 of mu1 ds, k st square times the L2 norm. So we have, therefore, here an inequality of the L2 norm of AF in terms of the L2 norm of F. And this means that if this expression here, and let me call this double integral as C0 square, if this constant C0 is finite, we have a bound on the L2 norm of AF in terms of the L2 norm of F. So what we get is, our conclusion from this computation is that AF, the L2 norm of AF, it's bounded by C0 times the L2 norm of F. Mind that here we are computing the L2 norm of F with respect to mu1, while here we are computing the L2 norm with respect to mu2. But in any case, if this integral is finite, then A, it's a bounded operator from L2 to L2. And if we call this integral C0 square, what we get is that the norm of A, it's bounded by C0. So here we have, again, a sufficient condition on K for A to be a bounded operator from L2 S1 to L2 S2. So I want to give a slightly different condition on K for A to be a bounded operator. So I'll fix again F in L2 of mu1, and I want to estimate A of F, the L2 norm of A of F. And here I wrote S1, S2, but what I meant is mu1, mu2. I hope this is clear. So again, I fix a function f in L2. I consider AF. I want to estimate the norm of AF. And I will use the following representation of AF. So we are in the space L2. So this is equal to the supremum over all h in L2, whose norm is equal to 1, of AFH, where we are representing here the scalar product. So we have seen that we can describe the norm in terms of the bounded linear functionals whose norm are bounded by 1. In the case of Hilbert space, L2, mu2, it's a Hilbert space. The bounded linear functional are represented by scalar products with respect to elements of the space. So we have this representation for the norm. So if I want to estimate the L2 norm of AF, what I need to do is to estimate this scalar product. So let me write this scalar product, AFH. Well, by definition, this is the integral over S2 of mu2 ds AFS HS. Now, I have an explicit formula for AF. It's given by this expression. So this is equal to the integral over S2 mu2 ds, the integral over S1 mu1 dt of k st ft hs. Now I will use Young inequality, which tells me that AB, it's bounded by a divided by 2a squared plus 1 divided by 2a b squared. So this holds for all a, b real numbers and a positive number. Right? Well, this is obvious, so let me use this inequality to estimate this quantity. I will estimate this quantity by, so I will estimate this quantity by k st times a divided by 2 ft square plus 1 divided by 2a hs square. So now I have two integrals, I have two terms. So I'll estimate the first one and then the second one. So the first one is a over 2. And here I have the integral over mu1 of ft square, and that times kst. I want to estimate, so I'll change the, okay, so let me do it step by step. So I will integrate it first in mu2 and then in mu1. So let me first consider the first term, then I will consider the second one. So here I change the order of integration. Well, everything is positive, so I can change by Fubini's theorem. And I'm first integrating with respect to mu2 and then to mu1. Well, I need to estimate everything in terms of the L2 norm of f. So I will bound this expression by the supremum over t. So this is bounded by A2. The supremum for t in S1 of the integral of k s t mu 2 ds times the, what appears here, it's the L2 norm of f squared. So this is the estimate of the first term. Now let me estimate the second term in this piece of the blackboard. And here I will do the same thing, but I will integrate it first in t and then in s. So the second term is equal to 1 over 2a, the integral over mu2 ds. So this is in S2, hs squared. And then the integral over S1 of kst mu 1 dt. And again, I have here an expression which depends on S. I want to bound this expression by a function of the L2 norm of H. So I will estimate that by 1 over 2a. The supremum S in S1 of this integral and what remains is the L2 norm of H, but H, I assumed that the L2 norm of H is equal to 1, and so this integral is equal to 1. So the second term is bounded by 1 over 2a times this supremum. So I will erase everything. I'll just keep the two estimates I obtained so far. So up to now, we proved that the absolute value of this scalar product is bounded by a over 2, c1 times this norm square, plus 1 over 2a, c2, where c1 is this supremum, c2 is that other supremum, and I just realized that a, it's a very bad choice for notation, so let me change this a to gamma, and this inequality holds for all gamma positive. So up to now we proved this inequality where C1 and C2 are these constants. Well, this inequality holds for all gamma positive, so we can minimize that over gamma. So I can introduce here an infimum over all positive gamma. And now if you compute, well, that's a very easy computation. You have to minimize that of all gamma function, which is a constant times gamma plus a constant times 1 over gamma. And what you get from this computation is that this expression is bounded by the square root of C1, C2 times F2 square. And so that, well, this is equal to the square root of C1, C2 times the norm of the L2 norm of F2. And so what we proved is that, well, this is a uniform estimate in H with functions H in L2 whose norm is equal to 1. Therefore, this supremum is bounded by this expression, and this means finally, so what we proved is that the L2 norm of AF, it's bounded by the square root of C1 times C2 times the norm of F. Which means that if I call C0 this expression, so C0 it's the square root of C1, which is this constant, times C2, which is that other constant. So if these two quantities are finite, and if I call C0 the square root of C1 times C2, what I get is that A, it's a bounded operator from L2 to L2, and that the norm of A, it's bounded by C0. So we have a different condition on K, which guarantee that A is a bounded operator from L2 mu1 to L2 mu2. And with this example, I conclude these examples.